Hello, hello. If we could all take our seats, we'll get this session underway. All right, plenty of room here, and we got the two screens, so you can find a great place to sit, excuse me. Well, I'm excited about this fourth breakout session. I think, rolling from the last one, I think we're going to dive into some more of the topics you heard about last session if you stayed in this room, and even some of the topics from the other session, because I caught a little bit about that. But really starting to get into industrial heat pumps, which are promising technology for A, electrification, and B, a lot of the low temperature processes, particularly those ones that we see in the state. So we have a really great lineup of speakers spanning research and analysis to industry and talking about what folks are actually, projects that are being implemented, to technology developers to talk about what technologies are being developed. So we're gonna get us started with Jibran Zuberi. Jibran Zuberi is a research scientist in the Energy Analysis and Environmental Impacts Division of the Energy Technologies area at my home institute, LBNL. Jibran and I work quite closely together, and I know you're gonna learn a lot from his talk. He has a background in polymer and petrochemical engineering with a master's in sustainable environment and energy systems from Middle East Technical University in Turkey, and a PhD in environmental sciences from the University of Geneva, Switzerland. I didn't know that about your master's, Jibran. We've been working for 5 years together, so there we go. Jibran has research experience from working on topics related to industrial electrification, process heat integration, energy efficiency, integrated energy systems, and so on, and has been at LBNL since 2021. Currently focusing on developing decarbonization strategies for industrial systems, identifying limitations, risks, and benefits of emerging clean energy technologies, and highlighting key targeted R&D research development deployment opportunities. He is also the author or co-author of more than 30 scientific journal articles, conference papers, and technical reports, though the story certainly isn't written. That's just the beginning, so there are many more to come. Jibran, take us away.
Thanks, Prakash. Once again, good morning, everyone. I'm Jibran Zuberi from LBNL, and I'll be speaking about one of the studies that we performed rather recently on industrial heat pump applications in US manufacturing. This is the outline that I will be covering through my presentation. So starting with a brief overview, followed by industrial heat pump applications in US manufacturing, and I'll end up with some of the opportunities for future work from the analytical perspective. So when we talk about industrial energy demand in the U.S., nearly half, 50% of it is in the form of process heating. And if we break that down further by industrial sectors, then all that process heat is really concentrated in 5 sectors. So nearly 86% of the total process heat is consumed by these 5 sectors, like refining, chemicals, iron and steel, food, and paper. Here on the right-hand side, you're seeing the plot that is disaggregating or separating the process heat demand for steam generation from the direct process heat, where you're combusting fuels for your core industrial processes. And you can see that nearly half of the process heat demand is for steam generation or hot water production. And in the plot on the left-hand side, you're seeing that the energy demand for hot water and steam generation is broken down by individual states. These are the top 20 states, industrialized states here in the US, and California is consuming the energy demand for hot water and steam production. I mean, it is the 3rd largest, and mainly because the type of industry, for example, food and refining, paper, they all are high on steam demand. Now, talking about the process heating system, so on the right, that's a typical process heating system where you have industrial boilers generating steam, hot water, and then combusting fuels for direct process heat to be supplied to your core industrial process. And then on the other side, this is something that we have been exploring. So when we talk about electrification, there are a range of technologies, but steam, which is like nearly half of the process heat demand, could be electrified with technologies that are already getting matured and are in the early stage of commercial deployment, including electric boilers, industrial heat pumps. And so yeah, when I started at LBNL, the first report or the work that we did was on electric boilers that is published. I mean, if you're interested, you can see that. Next, we did on high temperature heat pumps or industrial heat pumps. Some of the work that we did in that space, I'll be presenting next. And we are also exploring some of the flows here on the other side, but that's not the topic for today. So industrial heat pumps, what exactly are they? I'm sure most of you are aware of it, but just in case. So industrial heat pumps basically involves a refrigerant that absorbs heat on the evaporator side, compress it to a higher temperature and pressure, and release it on the condenser side to a sink or a process at the desired temperature. And the efficiency of industrial heat pumps is measured in terms of coefficient of performance, COP, which is a ratio of heat delivered to the electricity input or work done. So industrial heat pump applications in US manufacturing. This is the report that I was talking about. So we looked into 13 different industrial processes that for which we found good amount of data to study the specific applications of industrial heat pumps in these systems. And one thing I would like to mention that it's a conservative study. And when I say conservative, I mean that the heat source for these heat pumps was assumed as ambient. So we didn't look into the waste heat resources that are available from these facilities, because waste heat is very site specific and the amounts could vary substantially. So it was very difficult to generalize those cost curves, composite curves for applying the pinch techniques and see that, okay, how the COP varies. But that is something that could be done in the form of case studies once we start applying it for the individual facilities. And I think some of the colleagues are already working, I think Prakash, yeah, and Kelly's, Professor Kelly's colleagues. So instead of presenting the individual cases for all those 13 sectors, one example that I'm presenting today is on red meat processing. So in the table, you're seeing all the unit operations that are performed for red meat processing. And the ones highlighted in green are the ones which are suitable for industrial heat pump applications because they require steam or hot water at temperature that are suitable for industrial heat pumps. I'm not going into the details of the design, but we came up with a conservative general design to supply heat that is needed for these specific or particular processes. And here are the results. So for energy savings, but before that, let me, you can notice that there are a couple of scenarios, so scenario 1 and 2. Scenario 1 is where we are only looking into the hot water production, because heat pumps have been existing for quite some time now. The technology for delivering temperatures below 100 degrees is somewhat matured, while the ones which are delivering higher temperatures of steam, like over 150 or 120, I mean, they are in the they're in the early stage of commercial deployment. So that's scenario 2. So we wanted to make this distinction and see that, okay, how much of the impact of the current technology that is more established can make, and what is the potential for these technologies that are getting matured, and I mean the current state of the art. So we see that the final energy savings goes down significantly, but your electricity demand increases. So it's really important that your electricity grid decarbonizes at the same time. Otherwise, in terms of CO2 savings, the impact is not going to be that much. Final energy savings could be up to 50% in red meat processing. And these are the same results, but expressed in terms of CO2 emission savings. And you can see that, I mean, up to 90% of the CO2 emissions could be saved if the grid is decarbonized. But one thing I would like to highlight, the very first one in 2021. So even with today's grid emission factor, the efficiency of industrial heat pumps, which is, by the way, we are as I mentioned, that we are doing this conservative analysis. So even if we don't consider any waste heat resources and rely on ambient heat, you could still save a significant amount of CO2 emissions. So if you're applying pinch techniques and the grid is also getting decarbonized with time, the emissions savings are going to be increased drastically. And these are the results for all of the 13 sectors that we looked into. So on the right-hand side, you can see that these are the savings for fuel energy savings. So I would like to highlight a couple of sectors like canned fruits and vegetables, where you can save 100% of the fuel energy, because the process has the potential to be completely electrified. Similarly, when it comes to final energy savings, depending on which process it is, you could save up to 30 to 65% of the final energy from these processes. Sorry, I'm keep on pushing the wrong button. Okay, when it comes to the cost, I will not go into the other equations, but the very first one is specific cost. I've highlighted the benefits one. So when we talk about annual benefits in that formula, it is the cost savings due to changes in energy prices as you implement industrial heat pumps. So if the benefits benefits are expressed with the negative sign convention, which means if the benefits are more than your cost inputs, then the expression would become negative, and that's what we want. We want the cost to be negative so that it is cost effective. The industrial heat pump applications are cost effective. And despite the high energy saving and CO2 saving potential, you can see in the right-hand side plot that none of the cost for these sectors is falling below zero or horizontal axis. And but we also perform the sensitivity analysis to see that, okay, which variables affect the most, I mean, these costs, and I mean, how the cost varies if we make changes to those variables. So what if the natural gas prices increase by 50%, or electricity prices decrease by 50%, or the heat source is available at a higher temperature, let's say 40 degrees C. So we see that the costs are decreasing substantially, but still they don't become negative. But once we look into the impact of all these variables collectively in the combined scenario, we see that the costs start to become negative. So this shows that, okay, we need to work on all the fronts, multiple fronts, in order to make industrial heat pumps applications cost effective. And talking about the financial barriers, so really the barrier is this ratio, electricity to natural gas price. I mean, we need to put it down, otherwise industrial heat pumps are going to be very expensive. So industrial heat pump market, which is more not really established, but getting established in Europe, they have this ratio of around 2.24, while here in US, for the weighted average for the US it is around 5, while in California it is around 6. So it's quite high. This needs to come down. So as I said, we need to work on multiple fronts. And then I think, I don't know if I have time, but very quickly, as I mentioned, we at the facility level, for optimal industrial heat pump integration, we need to apply these pinch techniques, as someone was also mentioning it in the previous session. But in literature, you will see that some case studies have already been studied, but where it gets interesting is when you have to study industrial heat pump integration in batch processes, because there's a significant time variability there. And this is something that I've been discussing with some colleagues, also Professor Kelly. And we still need, we are yet to secure some funds to execute this sort of analysis. And that is it. Thank you.
All right, well, we'll do the presentations, and then we'll have leave some time for Q&A at the end. But thank you for that, Jibran. Next up, we have Stefan Hamlin, who is the Business Development Manager for Sector Coupling Solutions at Danfoss. Sector Coupling Solutions is the global leader in coupling solutions to further the goals of electrification and carbon reduction. He works with the North American team for Sector Coupling Solutions on heat pumps, energy transfer, heat reuse, and electrification, all very topical for the current market and future growth with Danfoss. Stefan previously worked as an Army crew member in the U.S. Army, reaching in the final rank of Staff Sergeant, accumulating 3 combat deployments to the Middle East and several other deployments across the globe. After 10 years serving his country, Stefan embarked on a civilian path of mechanical engineering and his role in developing a better, stable, and functional future. He's worked in several roles, from designer, design engineer, and now business development manager, working to bring heat reuse, energy transfer, free cooling, and hydronics knowledge to North America. Stefan, take us away, and let me make sure your slides are. There he is, but more importantly, here he is. Thank you, Stefan.
Oh. Good morning, everybody. Well, I'm Stefan Hamlin, and you heard my bio. I'm just me, working for Danfoss in sector coupling. And what we do is we have a broad portfolio. Wait, did I go to the right one or the wrong one? Okay, so pretty much what we have is a broad portfolio of all the pieces that you need for the heat pumps, for sector coupling, for everything to be brought together as a holistic solution, not just a small part of the whole solution. We have a holistic look at it. So this is pretty much a multifamily housing, commercial buildings, family homes, food retail, which is a big one, industrial process, and we really like the industrial process as well. So options to enable the ultra-efficient climate control is electrification is ready, optimization, maximize your energy efficiency, eliminate hot spots, and the smart reuse of wasted energy sources. And that's where I really come in, is to the So why is the market focused on heating electrification? Well, it's inefficient, very inefficient. And so what we have determined overseas and bring this over here to North America is our efficient way of moving forward for the decarbonization process. We have 35% operation cost reductions and 60% emissions reductions off the bat. So one of the issues that we do have is supply and demand, and how do we bring those together? Through energy storage, thermal storage, we're also working into that as well. There are several solutions that are available for this disconnect resiliency risk, including both supply side and demand side storage, enabling right through in those unavailability periods. What we believe is that everything is linked together. So it's not just a heat pump, it's not just a small solution. It's everything has to work together in order for you to become decarbonized and electrified for the future. So one of the challenges that we have is Danfoss's CO2 neutrality in 2030, enable low carbon campus heat via heat recovery. So you take a look that we have natural gas, heat pumps, cooling water, compressed air recovery, district heating, data centers, L5, and heat pumps. And you can see the annual heat consumption for Danfoss Norberg campus, the degree day adjusted. So over the time, we have reduced all the way down to 2024, 11.152, or I'm sorry, 11.512, and for the natural gas, all the way down to 9.683. So one of the solutions is we have retrofitted our data center with water heat pumps. So the original data center cooling system didn't have the heat pump, they just had a buffer tank and some other solutions involved into it. Well, we added a heat pump into it with a 43 and 67 for our things. We had a series counterflow compressor for the optimization of that system. And this is what we came up with at the end, which would give us a 43C in, 43C in, down to 55C to 67C back out. And to the other side is 20C, 20 AC going in and 20C out. So we have the medium and the high. These are the compressors that you can see that we utilize for the system. Also with this performance, at 20C, we're at 5.7 COP. And with that 20C in and 67C, which is a higher temperature going into it, with the 5.3 COP, we'll get a 9.5 COP at the end of that. Solutions of variations. I'm sorry, you can't hear me. I'm sorry about that, guys. Solutions variations. How else can the data center's heat be reused? With the heat pumps is that we have the indoor agriculture or recirculation for your aquaculture, or fish farms, anything else like that. Facility cooling and heating recovery. For the initial phase that we've eliminated one 2,700 ton steam chiller, one backup demand response, and replaced it with 1,500 and 600 ton electric chillers, and 9 by 215 ton water-to-water heat pumps. This has created a COP of 13.5 and a 50% reduction in condenser pump tower fan energy. And this goes on to the schematics and the P&ID of how we've come up with this solution and how we're working for it in the future. It also ties on for the, if you take a look at the bottom left, heat storage, level cooling, recovery to heat, and the demand. So it tie in base floor cooling loads to the condenser ambient loop recovery units. Also ties in the data center cooling and heat recovery, replacing adiabatic chillers. Retrofit the data center chillers to heat recovery stations, recovering heat to facility and external use. And this is what we've come up with the initial plan, and the solution is going to be coming up. For our solution to the dry coolers, heat recovery stations, heating domestic hot water, all the way down to a 375-ton 12th floor heat pump that goes back into the system. This will also incorporate neighboring loads and can help out with the neighboring loads. Additional campus heat recovery projects to hydrogen production is one thing that Danfoss is really big into. You have your 70% electrolysis efficiency. I apologize about my pronunciation. 30% waste heat recovered from the system. And your waste heat does increase further when paired with hydrogen fuel cell for on-site power. Data center integrated cooling heating for own use. So if you have a data center in the side of a building or on a campus, you can utilize that for yourself. You don't need really, unless you produce too much heat, you can give it to an off-taker if this needed. So this is our solutions that we've actually come up with. This is the hospital electrification retrofit that Danfoss has completed with a district cooling plant, central utility plant, and district heating CHP plant. Some of our solutions are an 8.8 megawatt 75C heat pump with the dry cooler, using the existing 6 megawatt water-cooled district cooling chillers, and preload existing CHP district loop with 8 megawatt cooling recovered heat. This is the water-cooled chillers, the water heat pump. So we've taken out that chillers, taken out one of the heat pumps for that, and added that into the full system, and gotten rid of our your plant, your boilers, and utilizing that the hospital as a base load for the heat pumps for the rest of the system. Solution is a performance for a 4 megawatt hospital cooling example. The distributed application is the benefit is the hospital cooling and district heating. It's a symbiosis system, so it has a total efficiency ratio. From the cooling to heating to integrated hospital cooling, heating, and district heating system. A dual use heat scenario per critical demand hospital and district. So it goes from 6.2 COP, and we can get it from all the way to 4 COP, 3 COP, 1 COP and less, depending on what you're going to be utilizing for the boiler system or water heat pump. Heat recovery retrofits, also we have 2 systems that we're utilizing work that's coming to North America is your grocery chain refrigerant small scale, approximately 500 kilowatts, maybe a little more or less. Also to your large scale data center heat recovery systems. The large scale is my bread and butter, that's my baby. Developed that for several systems over in Europe. And that comes in 5 to 5.5 megawatt systems in large containerized modular systems. This is what a containerized system looks like. Think of it as just an extremely large heat transfer unit. So an energy transfer unit, heat exchangers, pumps, controls, heat meters, everything that goes on to a regular energy transfer station, scaled really big. And then the refrigerant heat recovery retrofit system that we're using for most refrigerant in Europe, we're bringing it here for CO2 in North America as well. And it's a very efficient way to capture that CO2 from your grocery, put it back into your system, and put that free cooling back in. These are biogas, some of the opportunities, biogas plant that we've had. There's another one is the boiler flue gas scrubbers that we utilize. This is a refrigerant HVAC warehouse system integration that we brought up the 88 chillers and water heat pumps that we utilize. So the benefit factors of this are the immediate temp refrigerant recovery. Savings 20-year megawatts is about 124,325 megawatts over 20 years of the year saving. So total is about 133,389 megawatts per 20 years. Consumer goods process improvement. This is with the water heat pump replacing the steam heat boost. Electrification and parts bath that we've utilized here and in South America as well. So we utilize our own Sondex gasketed plate and heat exchangers, Grundfos pumps, because I love Grundfos, hydronic macro channel coolers, back to the parts bath, and a water heat pump. And then with the equipment, the boilers, the heat pumps, also with the regular heat pump, you get the COP of 4.6 at the end. This is another biofuel production energy recovery that we've utilized. For the tanks that we've taken the heat pumps and also the ambient loop that was already in there for the heat storage, also going back into those tanks because they weren't circulating enough heat and then putting it back into the system. We're taking that heat back from that system and reintroducing it back to the tanks as a heat recovery, heat loss capture. This is a cement plant kiln that we use for recovery as well. I know everybody's really big into the cement right now, and especially over in California, this is one of the processes that we've implemented. And then heat recovery from sewage water plants, and we're also using a lean heat, which is an AI-driven system to see what is going to be the best performance of your whole campus. Subway heat recovery, we use these in London, and we have one in Manhattan as well. We're also trying to move this to other places. Microchannel coils that we utilize along with our water heat pumps. Why water heat pumps and high heat recovery temperatures are critical. At the low, 120, roughly 120 per megawatt hours, and then at the highest, 360 per megawatt hours. In critical facility cooling and heat recovery systems, we believe that each one of these has a very, is critical for heat pumps, that you can recover a heat pump, put that back into a grid if you have a grid you're utilizing, or back into the building itself. The data center is huge for us. Food retail is another big one for us. Hospital heat recovery, industrial process heat recovery, and centralized generation heat plant. And then Danfoss hydronic systems portfolio, just to let you know, we have a huge portfolio again. And thank you.
All right, thank you, Stefan. That was wonderful. Got to see a whole slew of solutions, particularly benefiting from waste heat and reusing waste heat. Next up, we have Ryan Orozco from Cascade. He is a senior engineer with Cascade Energy with 15 years of experience as an industrial energy efficiency consultant and has delivered utility demand-side and corporate direct energy management programs to hundreds of customers and facilities in a wide range of industries. He specializes in analyzing and optimizing industrial HVAC and refrigeration systems. Ryan holds a bachelor's from the University of Portland and a master's from the University of Utah, both in mechanical engineering, and he is a licensed professional engineer in Oregon. Ryan, if you please come up to the stage and take us away. Thank you, Ryan.
Good afternoon, everybody. So I'm Ryan Orozco, senior engineer with Cascade Energy. So today I'm going to be talking about a recent market study we performed for the Bonneville Power Administration in the Pacific Northwest, looking at industrial heat pumps. So the motivation behind this, the BPA was very interested in understanding the technical potential of heat pumps in their market, and also they wanted to know how current energy efficiency programs can deliver heat pumps and make it an option for their customers. So as you can see from this tree diagram, there are 5 industrial segments that account for about 2/3 of the electric load in this region. Pulp and paper, wood products, food processing, chemicals, high tech. So for this reason, we focused the study around these industrial segments, but also compared to the other segments on this list, we thought they had the highest percentage of low and medium temperature heat loads that could be served by heat pumps. So the first thing we did, we chose 10 sites to participate in the study, 2 sites in each of the 5 segments. We focused this on a couple different criteria. One of these being how representative the site and the systems at the site were of the broader segment. And second, how motivated these sites were to implement energy efficiency projects. So as you can see, 8 of the 10 had a history of strategic energy management. 5 of them actually had on-site energy managers. So we were pretty confident that they had a good culture of energy efficiency and that this could translate to heat pumps. So as we know, from a high level, heat pumps use electricity to move heat from one area to another. In an industrial setting, this looks like moving heat from a waste heat stream to a process heat stream, from a low temperature source to a higher temperature sink. So we spent about a day at each of these 10 sites, and we really focused on identifying the main sources, the main sinks, and evaluating if we could link those together with heat pumps. So when it comes to the analysis, again, keep in mind this was a scoping level effort. We had a couple main assumptions. One of these was around the COP, or the coefficient of performance we used in the analysis. So we based it off of this curve fit from this actual data from heat pumps. So just basing it off of lift, the difference between the source and the sink temperature. So with that, we were able to calculate the energy use of the heat pump and subsequently the energy savings. Secondly, as far as cost goes, we use this table from ACEEE for capital costs of heat pumps, types of heat pumps. We focused on mechanical vapor compression, closed cycle. We simply used an average of these two costs in the analysis and across the board for all the heat pumps. And so with that and the energy savings, we calculated a simple payback for this scoping level analysis. So some of the main opportunities, we came up with 5 heat pump opportunities. Of these, a couple were domestic hot water, but the vast majority were industrial heat pump. Looking at this table, you could see that there were a variety of sources and sinks. I wanted to point out some of the commonalities. One of these is using air source as a source, and then the other one would be using or a sink being process heating water, which was fairly common in some of the segments. So when it comes to economic viability, again, we're looking at simple payback. The projects we found in high tech and chemical were the best looking projects using that metric. Pulp and paper and wood products, some projects looked appealing, others didn't. And this was largely driven by the use of hog fuel boilers in some of those sites and the fact that a lot of that hog fuel is sourced on site. So it's a very low cost fuel. So switching to electricity just did not make sense at those sites. And then food processing was a bit surprising. We know that food processing is a good area for heat pumps. I think this was more of a function of the sites we chose and the location. I'll get more into that. So we took a look at the overall energy spend savings in each of the segments. So we looked at 3 different scenarios. The first one being just the existing situation, which was largely using thermal fuel as an input, and there was some electric resistance. The next scenario was converting all of that to full electric resistance. And then the third was converting the existing to all heat pumps. So you could see, converting to all electric resistance was a major increase in annual energy spend, whereas converting to all heat pumps resulted in pretty good savings for the most part. High tech and chemical had the highest percent savings, but pulp and paper and wood products, those projects were just larger in magnitude, a little bit lower percent savings. So what were the top IHP takeaways from this? What did we learn? So I boiled it down to 4 takeaways. The first one is there needs to be a focus on what we're calling kind of the heat pump economic wins. So these may not be the largest heat pump projects, but we felt like these are the projects that could deliver savings and quick wins to really get traction in this market. So this was broken down into a few categories. So one of these was, the situation where you've got electric resistance in the baseline. So this was at a chemical site, just a tank of hot water, 180 degrees F, and just heating it with electric resistance heat. So this provides a great opportunity just for converting to heat pumps right away. And this was fairly prevalent in these 2 segments. The next would be looking at air source heat pumps for smaller loads. So the sites we looked at in chemical and high tech they did have smaller process heating loads. So we thought it would be possible to use air source heat pumps, and even locating that in an engine room with fairly warm temperatures would provide, not the best COPs, but decent COPs. And lastly, let's not forget about heat recovery. So not a heat pump measure, but a lot of these sites did not have any air source heat recovery, or it was non-functional. So this could be a more cost-effective solution for using high-temperature waste heat. Second key takeaway, so spark gap is important. This is the ratio of electricity to gas price. In this case, natural gas, but and any thermal fuel. We had some biomass projects as well. So the lower the better here for heat pumps. And as you can see, most of our projects were in the state of Washington, where it is fairly low. But as you can see from the graph on the right, with spark gap on the y-axis there was quite the range of spark gaps even in Washington. But it's interesting to note that for spark gaps below 2, those projects delivered the quickest paybacks, the smallest bubbles there. And that was even for a range of lifts. So we know that lift is a key factor that drives COP. But in this case, as long as the spark gap was low enough, the project looked pretty good. So I think that's a key takeaway. Some of those larger bubbles were those food processing sites, which had a higher spark gap. So that's why those projects didn't pan out. The next key takeaway is to we need to maximize the projects that deliver greenhouse gas emissions reduction. So you could see, 4 of those 5 segments, the savings were above 75%, which is largely driven by the conversion of thermal fuel to heat pumps. A very small sliver of that is, the existing electric resistance to heat pump. So that there should be a focus on those projects. And you'll see that, the wood products sites had a great increase in greenhouse gas emissions, which was largely driven by hog fuel boilers. Again, so burning hog fuel, you're burning, releasing biogenic CO2, which was previously absorbed CO2. So when we're accounting for that, we're just looking at the methane and the nitrous oxide. So it's a negative savings in those cases. Fourth big takeaway, there's a need to leverage policy drivers for implementation. So this was funded by the BPA, and they were very interested in knowing how they could provide utility incentives to promote heat pumps. One such way was by comparing the heat pump to a less efficient electric alternative. So that's kind of the road that they're going down. The second was state and federal regulation. Most of these sites, like I said, were in Washington, where there is also a CAP program on emissions. That only applied to 2 of the sites, 2 of the larger pulp and paper mills. But when accounting for that cost of emissions, which I think the current auction price was $40 per metric ton, that cut the payback in half. So that's a big factor to consider. And then corporate greenhouse gas emissions goals. Some of the sites had near-term goals, 2030. Other ones had longer goals, 2050. But they were very interested in knowing how heat pumps could help them get to those goals. And just a few next steps. We plan to release this paper, by the end of Q2, so you could, see more of the detail about the projects that we identified. And then also, we want to complete more detailed analysis and studies for the measures that look good and for the measures that companies think they might move forward with. So that would include, hourly energy analysis, getting vendor pricing, and then also putting more focus on greenhouse gas emissions savings as well as non-energy benefits. So, thank you.
Thank you, Ryan. That was wonderful. I think those 4 key takeaways are going to prove very useful to all of us here. Next up to bring us home right before lunch is Herman Robledo, who is the industrial heat pump sales manager at GIA Heat and Refrigeration Technologies. Previously worked for General Motors as a design engineer, Alfa Laval as heat exchanger and separation sales manager, Johnson Controls as designer, sales, and service manager for Latin America North, and as Latin America sales manager in refrigeration, gas compression, CO2 technology, and heat pump technology for Copeland. So a very nice, illustrious career that began in Bogota, Colombia, where Germán has lived in the United States for 25 years. He comes to us with a Bachelor's of Science in Mechanical Engineer from the Universidad de America in Bogota. Do you need, you all set with the? I'm set. Okay, great. Thank you, Germán.
Good afternoon, good morning, everyone. I only have 5 minutes. Let's see how we can manage this. Are you hungry? Okay. So I was invited to show you about heat pumps in the US. We've been selling heat pumps for the last 2 years. Heat pumps started making sense every time that our corporates are saying decarbonization targets, 2030, 2040, 2050, right? So we've been doing some cases in the US finally because we've been doing this for the last 10 years. It was very difficult because of these low gas prices in the US. So basically what's going on is the decarbonization. You heard this morning about the Department of Energy, the roadmap to decarbonization. 4 steps or 4 pillars, that's how they call them. Basically you had the energy efficiency, the electrification, the low carbon fuel switch to biomass or hydrogen, and then the carbon capture, utilization, and storage. On those things, if you start doing that from nothing to 2050 and start doing all these 4 steps, eventually you're going to get to 2050 carbon neutral. Ideally, the heat pump is one of these low-hanging fruits technologies because it's one of the things that is hanging around today. It's been for the last 10 or 20 years. Unfortunately, Europe has been ahead of us for the last 10 years because they need more of these heat pump technologies than the US. Now, heat pump in the US is making sense for all the companies. So as you can see, basically, as you can see technologies, you can see electrification technologies. You're going to find like induction furnace, microwave, heat pumps, anything that you need. So what happens is that you have different companies, mainly food and beverage. You see those thermal needs. The US has a lot of these heat demands. 40% or 46% of that is in the low grade. They call it low grade, anything below 150 Celsius. It's typically food and beverage. Obviously, we have also auto industry, resins, chemical, pharmaceutical, oil and gas. But basically, food and beverage is the most low-hanging fruit on the heat pumps because they have these 2 temperatures. You have a temperature coming in, your heating process, you're heating, like making steam to heat water 2 minutes. Sorry, guys, we got to cut it off. And then you have this energy out coming out like refrigeration systems, right? If you become smart about that, you can combine these 2 energies and replace those loads made by the boiler, now have them make it by the heat pump. So the heat pump has been something that is making sense today. It's technology has been around, man. Now people are talking that it's new technology. Well, it's not. It's been there. Like a steam heat pump. Some people are just posting things on LinkedIn saying steam heat pumps is new. No, it's not. It's been there. Even heat pumps, steam heat pumps were in the US for like in the 1970s, but it stopped in the 1980s, right? So basically, we know there is 2 technologies. You have the closed cycle technologies, you have the absorption technology and compressor technologies, and then you have the open or semi-open cycles. You have basically recompressing steam. We call it MVRs, mechanical vapor recompression. So basically on these technologies, basically you need a heat source, come in and a heat source. We only got 1 minute left, so I don't know if we need to stop or we continue. You guys decide. Okay. Yeah, so going back to these technologies, basically you need a waste heat technology. You need some waste source, basically to the heat pump, and I'll raise it up in pressure and temperature depending on what technology you're using. So you know that it's basically competing between combustion energy. Now you turn that famous boiler into electrical heating. That's where the heat pump comes into the game, right? And basically you're combining the heat that happens of compressing a gas with the heat that you combined of waste source. You add those two, and now you have more units of heat available and produce more heat than the combustion energy. So what happens is that you have different sources. You can use air source. You can have water, like river, ocean, lake, anything, ground. Geothermal loops is happening a lot. Any waste heat coming from a process, you get it into an evaporator, start having this refrigeration cycle inside the heat pump. We call it refrigeration cycle because it's still a compression cycle. And then that heat goes to a heat sink. And that's where you start making hot water needs or something like that. Depending on the temperatures and process, you have different temperatures. But today, current technology available, and basically depends on refrigerants, you can get today up to 95 Celsius water leaving out the heat pump or 203 F. You can go into different processes like cleaning in place, pasteurization, blanching, evaporation, drying, things like that. You want to go over the steam line, higher temperatures, it's got to be with a different technology, or in the heat pump using compressors has to be with a different refrigerant. So that makes a choice of refrigerants. Some refrigerants is going to be based on your critical point, critical temperature, that refrigerant. So basically, that defines the heat pump, and it's going to define the heat pump cost, the heat pump technology, and the heat pump COP. The higher the pressure of that refrigerant, the higher the cost of the heat pump because you're running with components rated at high pressure. The lower the pressure of that refrigerant, it's probably going to be a lower cost heat pump, but at the same time, you're sacrificing COP. So you got to find that break point, which one you want to choose. But also now you're falling into a lot of these ASHRAE classifications. That's a A1 or B2L or A3, depends on toxicity, flammability. And also if you're running into low temperatures like making hot water or making steam temperatures. So what happens, we're using ammonia because we're still finding that ammonia is one of the best refrigerants so far. Ammonia has one of the highest content as far as heat pump capacity, or we call it volumetric heating capacity. This is a comparison between some of the ammonias and freon synthetics or HFOs, where you can see the COP of ammonia is always the highest content. Unfortunately, ammonia is toxic, so you have to have some management around ammonia. So the efficiency is driven by different things, but basically you're comparing two efficiencies, your boiler efficiency or gas combustion efficiency versus an electrical-driven heat pump, right? So what happens on a boiler, you put X units of fuel inside that boiler, but because of the boiler efficiency, you only get less units out. On the heat pump, you're combining the heat source plus the heat of compressing a gas. Those are added, and now becomes the units out of the heat pump. So you have less units on the boiling or boiling process, and you have more units on the heat pump process. On the heat pump, we call it COP shaft. That's on the shaft of the compressor, and COP line. That's because we start adding any motor losses, any variable frequencies losses, or any losses that are also part of the heat pump efficiency. So the efficiency is going to be driven on your temperature lift. The higher the temperature lift, the less efficient the heat pump. It's going to be a low COP. The smaller that temperature lift, the higher that COP. So if you have like temperatures about 140 F water, yeah, great, you're gonna get a great COP. But if you want 190 F or 200 F water, you're gonna have a small COP. Also the capacity, how much kilowatts, we're calling kilowatts as heating capacity, don't confuse that with electrical kilowatts. So the larger the heat pump, the less the COP. So this is a case where I've been seeing companies calling us for heat pumps and different companies on different states. And let me see if I can get it more in a magnifying way for you. So if you look at efficiency of say that you need 1,500 heating capacity and you have a 90% efficiency on the boiler, and you're running 18 hours a day, 6 days a week, and 50 weeks in the year, that's a total of 5,400 hours per year. Your efficiency to make that 1,500 kilowatt, you need to consume on the boiler 1,600 kilowatts. That's a total of 9 million kilowatts per year. Say that you get a heat pump or COP of 3, you only need 500 kilowatts to make that same 1,500 heating capacity. That means that you're only gonna consume $2.7 million in energy on the heat pump. If we figure that the heat pump is gonna cost you capital between the cost of the heat pump and installation costs, about $800 per kilowatt, you come around investing about $1.2 million or $2 million in total. So you take the total operation of the electricity, different rates that you get, like Lugo, Texas, Nevada, Trudeau, California, Fort Montgomery, Colorado, Jeremy, Idaho, the electricity price, the natural gas price, and then your spark gap ratios. Then you have your operation of that boiler per year, how much you're gonna spend per year annually on that energy. On the heat pump, your difference between those two energies. And then you divide that OPEX, right, that CAPEX by this OPEX, and gives you the return of years. You can see that the worst case is 40 years for the guy in Idaho, 18 years for the guy in Texas, 23 in Nevada, 10 in California, and 8.4 in Montgomery, Colorado. But if we raise that COP to 4, then these years start cutting back. And if we even raise that to 5, even it's becoming even better and better. And even to 6, now I'm getting into 9 to 11 to 9 years, even 4 years. So that what that means is that you need to find the best technology on heat pump. If you're driven by COP, you're gonna get your fast results. You're gonna have COPs. You're gonna have your reduction of emissions. So it's all around COP. And the reason I mentioned that is because I get phone calls from customers talking about this, but then when we show them a price, they get scared. They kind of reset back, and we were, were you looking for decarbonization? Were you looking for a price? We don't get it. So that's the point on this chart. So what happens is that a lot of these companies have refrigeration systems or chillers, and that's your heat of source, your heat of rejection of those systems gotta go to the heat pump. So the opportunity is taking that heat of rejection that today is being wasted on condensers or cooling towers, move some part of that heat and now send it to the heat pump and take that opportunity mainly in food and beverage companies. So we can see this, and we've done it. We have this portfolio where we have from the low capacity, we start in the 100 kilowatts heating capacity up to the 10 megawatts heating capacity. We can do different temperature scales up to the 95C. So we have piston heat pumps, we have screw heat pumps, we have a combination and custom made. All depends on application, on customers, and other things. So what happens here is that this is our typical heat pump. It's a skid where we mount compressor with heat exchangers, evaporator, condenser, subcooler, desuperheater. It's gonna vary in size and dimensions depending on size and capacity on the customer. Sometimes he may need 2 or 3 or 4 sets of these skids, or you may be just one set of these ones. So cases like this is a district heating case. They do winter hot water for district energy. They do about 85C or 180F in the winter time, but also in the summertime, they do 42F or 5C. So it's a combination what they call district energy, district cooling, and district heating. This is in Markham, Ontario, in Canada. We delivered this last year in summer 2023. It's already running, it's already performing. It's already working there, and it's a 4 megawatt. It's 2 sets, each one is 2 megawatts, so a total of 4 megawatts heating capacity. This is a dairy plant. Unfortunately, I cannot give you names because a lot of these companies is making us sign NDAs. We just delivered this in February, went to Glendale, Arizona. It's for a big dairy company, big dairy guy in global. It's 2 sets, 2 megawatts. It's 2 sets of 2 megawatts, 4 megawatts in total, and then making 95C water, a COP of 4.3. Next one, these 2 next ones are going to be delivered by May. This one is going to a dairy plant in Idaho. It's a 1 megawatt heat pump. It's gonna make about 80C water, 176, for COP of 4.9. The next one is going to a dairy plant. It's going to also, this one is going to Canada for 2 megawatts. They're making 180F water, 82C, and a COP of 4.6. This one, we just got it, is going to Georgia, a big brewery guy, 4 megawatts. This is probably gonna be delivered by December this year or January next year. Heat pumps are taking about 40 weeks lead time today. Unfortunately, it's not us, the compressor guy, it's the heat exchanger guy who's holding the line. So think about that. You need about 40 weeks from between when we get a purchase order and we deliver to you. Then think about 1 or 2 months between installation and then another month in commissioning. And this one, we just got it recently last week, 1.7 megawatt for a dairy plant in Canada. So when it comes to steam, we can decarbonize steam. Basically, we can make steam with heat pumps. Basically, you're looking at the different temperatures. You're making a hot water temperature and making steam temperatures. All depends on what refrigerant you're going to use. What ACEEE, when they came with this report, they decided to define them between natural refrigerants, hydrocarbons, and HFOs. You can see the temperatures around these, depending on the critical temperature, that refrigerant, how high you can get to steam lines. HFOs, just to give you some case, they can give you these high temperatures. The problem or downside that is happening is that a lot of them are becoming a big problem in Europe, and now it's coming into the US, where some of them have become part of a wash list or radar list, where they are part of the PFAS and TFAS problems, these forever chemicals that are a danger to human health and animal health and grounds. So the other factor when you consider it also is that when you manufacture a refrigerant, sometimes they make a lot of CO2 emissions. HFOs take about 3 to 6 times more CO2 emissions than making naturals. And also you have to account on your scope 1 and scope 2, what we call the fugitive emissions. HFOs needs to report it. Naturals, they don't need to be reported. So what's the choice? Well, if you need to make steam, go to hydrocarbons. Hydrocarbons could be pentane, butane, propane. So we have a demo site that we're building in Europe. It's a juice company. Ideal is to make steam. It's going to make about 3.5 megawatts up to 138 C steam, a COP of 3.9. This is going to be commissioned by September, October this year. Eventually, there were 3 jobs awarded in Europe, or 3 grants. One of them was spilling technology, the other was Maikawa Micron, and the other was GIA. All of us are using pentane or butane for these things to make steam. But today, there is no steam with pentane in the US, so the solution at the moment is to use an MBR. So I explained to you at the beginning that this is a second technology called MBR. Basically, what it does is you need to make steam at a low temperature, low pressure, and now you raise it up to pressure and temperature using these devices, like in this case, it's called a fan. They call it a fan blower or vapor fan. It's like a centrifugal fan blower that rotates about 15,000 RPM. And they're gonna scale your temperature by 8 degrees Celsius, 18 degrees Fahrenheit by steps. So you start like at low temperature, like 90 C, and you need to get to 120 C, you may need 3 wheels, 4 wheels. You need to go higher temperature, you need probably 5, 6, 10 wheels. So what happens in many opportunities is take that heat source that you have today, like the food and beverage refrigeration systems, put a heat pump to make hot water, and send water from the heat pump to an MBR. Basically, this is a flash vessel that is on vacuum. Water flashes or becomes from water to steam because it's a vacuum or negative pressure, and now you make steam. So this is a Heineken Manchester in the UK, where they have the refrigeration system making those glycol systems for the glycol side or cooling side or refrigeration side, and that heat was being wasted through condensers, and then you have the boiler making steam for fermentation and steam making hot water for the cat wash, pasteurizers, and cleaning place. So we converted that into a heat pump. We put a heat pump making 90 C water, and water goes to what is really need, hot water, and then water goes at 90 C, flashes, turns into a steam of 90 C, and it's raised by MBR to almost 130 C or 260 F. And that's how they're making clean steam without any need of a boiler or a fossil fuel. This is a pet food company in Norway. They need a drying tunnel for drying these pet pellets, where they turn that into a product, and it's already running as well. So basically, you can see the chiller side on the left, the heat pump in the middle, and the MBRs of these MBR wheels on the right. This is the flash vacuum vessel. So you can see it's a really small installation to make steam depending on the size you're looking at. This is kind of the performance they're looking today. They were able to get, depending on part load, a COP of 2.4 and a COP of 3.1, but to making steam at these high temperatures. So what's the barriers that we're seeing in the US? Same thing that always. The lack of knowledge, lack of understanding, the lack of how to integrate it into your process. Some are still high price technologies, incentives, fundings, right? The pilots or demonstration sites, unfortunately, the ones we sold, some are already in operations, some are going to be delivered soon, but the customer doesn't want that we share the information, so that's gonna be difficult to show you results or metrics, right? Domestic manufacturing, there is some companies in the US already making heat pumps. There is no need to import them from Europe or Japan. And the most important that always we see utility pricing. Utility needs to come in the game with a better path for the electrification. So the cost of the heat pumps are still high. Think about always $1 million around heat pumps for 1 megawatt. But what contractors tell me, depending on the installation, it may be installation cost of a ratio 1-to-1. You spend $1 million in your heat pump, you may spend probably another $1 million in your installation. But it may be also a ratio 4-to-1. You spend $1 million in your heat pump, you may spend $3 million in your installation. The price of the heat pump is going to vary. That's a big question. Why there's no like a rule for a fixed price? Well, there is not, because it may just use one heat exchanger, 2 heat exchangers, or 3 heat exchangers, but they can be rated depending on your living water temperature for different pressures. The higher the temperature, the higher the pressure, the cost on these heat exchangers. Then we've seen a lot of these retrofits or brownfields, existing plants where they have limited space. They always come back with a small space to fit 1 or 2 heat pumps inside that engine room. So the market probably needs to go to outdoors, but unfortunately heat pumps don't like outdoors. So you need to start thinking about making enclosures. And the last ones, every time we see capacities like 9 megawatts, we gotta go like 5 piston heat pumps in this case, or 4 heat pumps screw. But customer is gonna reject because first, he doesn't have a space for that, and second, it's gonna be very costly for him. So the number of heat pumps normally is gonna be 3. Anything more than 3, customer is not gonna buy a heat pump. Then the integration, you always need probably to start thinking about using buffer tanks on your heat source and buffer tanks on your heat sink. Buffer tank is gonna help a lot on the heat pump operation. It's gonna help you as far as partial loads, sudden changes, spikes, and any of these changes where you want from 100% down to 0%, well, heat pumps, they do that. Heat pumps go down minimum to 30%. You need that 0%, use a buffer tank. And buffer tank is gonna give you a heat pump operation without a heat pump 1 hour, 2 hours, 3 hours. Always think what's your backup when the heat pump is down, when the heat pump is not running. So probably it's gonna be your buffer tank, or continue using your boiler or put an electrical boiler. So this is a case of Coca-Cola in Europe. Pretty small video, and we're done with the slides, so hold your hungry. As the water tanks. This is the base for the heat pumps. That's what our heat pumps look like. This one on these videos are 2 megawatts. Now they're building the base for electrical boilers. That's it. Any questions or any comments? Well, I guess in lunch. Thanks, everyone.